So the Red River, yeah, favorite topic in here. I'm going to show then a very complicated graph. Some of you have looked at this graph. Some of you have looked at it and you've scratched your heads and you've gone, what can you possibly make out of this graph in here? Let's just walk our way through this graph a little bit, because I think it has some interesting features to it. It doesn't provide any particular answers in here, but I think it has some interesting features to it. So what it shows then across the top of the axis there, I'm looking at the lower part of the graph then on here, it shows the year going from October to December. And then what it's showing is the flow rates on the Red River, okay? So maximum discharge type of rates, flood discharge type of rates that we would get on the Red River in here would be colored dark blue on this particular illustration. And you can see then that there's a general swath going from the top of this graph down to the bottom where blue colors are highlighted, okay? So then they're highlighted through the months then going from March or late March then through June, okay? So this is the time then when we're all familiar, we're very familiar with it in this last year, had enough of it, when we have spring flooding in here, okay? And so we see that pretty clearly on this graph then that was prepared by NOAA for the Red River. Now, one of the interesting things about this curve, though, is you look way over to the left-hand axis of this curve, you mostly see then green colors and yellow colors. And those colors then are lower discharge rates on the river. But if you come up to this last year and the few years previously to that, what we see is that in October and November, we've got very high discharge rates on our river. And it's almost like if we have high discharge rates on the river, then we're guaranteed to have a flood in the spring, is what this actual data looks like. And then that is on the top, then that particular part of the graph is actually highlighted on the top that's on there. So now, a couple of things then in here. As we look down the graph and we look to low discharge rates on the river, and I'm going to talk about this in a minute as well, you'll see the red colors in there, and you can see those red colors then are for the years 1930 and in the 1930s. These are the dirty 30s, okay, that are represented. And we see very low discharge rates on the river during that particular time. But it's interesting that there does seem to be, though, as we come towards the top of that curve in there, it does seem to be some sort of change, a step-type change occurring in the high discharge rates on the river. We just don't see, in earlier years, those high discharge rates in the fall. It seems that these have been particularly common then in the last, say, 10 years or so, these higher discharge rates. So there's a question then you might have from this. You might say, well, is this an effect of climate change? Is this an effect of global warming that we're seeing then imposed on this record? Is this why we're seeing these changes on the Red River? I would say to that, we can't tell. There's no way to tell that. There's just not enough of a trend that's there to tell it. But it enables us to ask that question that's possibly there, that's on there. It does, though, get into, it allows us to get into the talking a little bit about some of natural climate change on the Great Plains and the effects that it has in here. And that gets into talking about wet and dry cycles in here. Well, clearly, the last several years has been wet cycle in here. And if we go back in the record, though, we can see then that in the 1930s, low discharge rates, this is obviously going to be part of a dry cycle that's represented. Drought then, it's the strong droughts of the 30s are part of a very strong dry cycle that's there. We can come up, though, to the 1980s in there, and we can see also shorter duration idea of a dry cycle. So we get a sense, a little bit of a sense off this graph, although the one I'll show you in a minute, much more of a sense, that we have this natural cycling in our climate of wet cycles and dry cycles. And from our region, not so well understood particularly, although John will have climate data to talk about this maybe. So Well, we are concentrated and we are focused, and we salute the city and the leadership of the city for the great flood fighting efforts that they've made in recent years in here, and how each time we get one of these events, they've improved their abilities to deal with the events, and it's quite magnificent what has occurred in the city with respect to that. But at the back of our mind somewhere, we have to keep in this notion, it's difficult when we're just coming off a really big flood, to keep in this notion in here that this river can get real low at different times, okay? So this happens to be an image then from the Institute of Regional Studies for the first part of the 1900s, and you can see the Red River in there, and it's pretty low, and it's probably pretty stagnant, and there's not much oxygen being moved around, and undoubtedly fish are dying, and it's smelly, okay, and in this particular image in here. But this is the river then that we get our water supply from in here. So drought then is the other side of this coin in the wet-dry cycle in here, that the city then has to be prepared to deal with into the future in here. And coming up to the year 2030 in here, I would argue that's probably going to be more of a problem for the city in here than dealing perhaps with the floods that we've been dealing with in recent years. So I just want to show you this graph. It's a highly simplified curve. It's derived, and so it is actually derived from real data. The real data in this case happens to be a series of trees that occur and grow out in western North Dakota. So this is for western North Dakota. Unfortunately, we can't show you a record like this for this eastern part of the state. So if you take tree ring records from the western part of North Dakota, you can get back to about the year 1600 or 1650. It's a long record of climate. The climate records that John Wheeler deals with in here probably go back in the order of about 100 years or 105 years, 110 years, something like that. This is a much longer look at climate that you can take then using a proxy, like a tree ring then, to estimate climate type changes. And so what happens in here then is when it's wetter in here, the tree is able to pick up more nutrients, the rings grow, and they reflect that particular climate change. When it gets drier, the tree can't pull up those nutrients, it puts on less woody tissue, the ring on the tree for that year becomes pretty thin in here. So you can track then the thickness of the rings, and they then are a measure of wet and dry cycles. And what you see in here is that through this period from about 1650 then, coming up to about the year 2000, where most of our records end, unfortunately, for western North Dakota, what you see then, there's a pretty rhythmic series of changes going from wetter to drier cycles that are in there. These are the wet, dry cycles that we talk about that are well represented then. And if you measure then, with the exception of the one that's shown in the middle there that goes from the little bit after 1800 to a little bit after 1850, most of those wet-dry cycles then have a frequency on them, if you want, a length on them then in there of about 20 to 40 years. That's the sort of cycling that we have on them. Now, at the end there then, what you can do is you can say, well, let's put another cycle on here and what would happen to it. And so the red that's on the end of this curve then is saying, okay, when will the next drought be if you use this record of cycles then from western North Dakota? And the answer you're going to come up to that on there, it could be relevant to Fargo in the year 2030 because it falls sort of right between 2020 and 2030 in here. Now, what we can't say, okay, what we can't say from these records is how strong the droughts are going to be. They could be 30-style droughts, which lasted then for several years, not consecutive, but for several years, or they could be much shorter droughts lasting 1 or 2 years. We just can't say that from this type of data that's available from these tree rings. We also can't say from this particular image, this is for western North Dakota, and by the time we come over then to eastern North Dakota, it's not the same, okay? It's different. But we have cycling in here, but there are differences in here, and we don't know enough about the science of this at the moment to actually make this information useful. It's possible in the future that some of the science may develop enough to make some of this data much more useful in terms of predictability. The other thing that's in here, though, that I think some of you are probably wondering about then in here is, that, okay, this is a natural series of climate changes. These are wet, dry cycles. If the climate is warming, okay, in here, what's happening to these wet, dry cycles? And the answer to that is we don't know. And you can, and nobody knows. You can go on to the EPA and their website, and you look at their region, and they talk about then how likely, it is likely then that what the effect of the warming will be on the wet-dry cycles is that the wetter cycles will become wetter, and the drier cycles will become drier. In other words, there'll be a stretching of effect. But nobody actually knows what that effect is really going to be, or whether or not there will be an effect. Okay, we just don't know that. So this is something that's sort of been in my, a bee in my bonnet, if you want, for quite some time in here. We do know then that the city is preparing for the possibility of drought into the future, and where then it might be able to get water supply to the city into the future. And of course, this is a lot more critical as the city has grown bigger. As the city continues to become bigger, it becomes more of a problem into the future. And so there are studies out there, and this is one of them then in here, and it seems to be, to me, that, and there are other people, Pat Sauerall is in the room at the back, and he might be able to comment on some of this for sure. It seems to me in here that for political reasons then we've opted to look at go to the west for possible help with this water supply. So this map that's on here then, what this map is showing is that if you take precipitation, annual precipitation, and then you extract from that the amount of water that's lost back to evaporation in here, what you see then, you see a series of isolines, and those isolines mostly are running north to south that are on here. And we can see then that in Minnesota, there's an isoline of 0, and then we actually have a positive value of 10, okay, off to the right. And then, but as we go across North Dakota then, we see negative 20, negative 30, negative 40. They become more negative as we go across to the western part of the state. And we know this, right? We know then that it's wetter in eastern North Dakota and Minnesota than it is in the western part of the state. The western part of the state is, to some extent, semi-arid in the western part of the state. So we know this sort of intuitively. But this pattern, as it turns out, holds up for about 10,000 years. These isolines will always head north-south. This is the way that the precipitation gradients are set up across North Dakota. So as we look then to supply North Dakota in the time of a large drought in here, what are we talking about? We're talking about going to Lake Sakakawea for water supply. I mean, this seems to be the preferred plan that seems to have come out of different studies in here. And even though we know then that Lake Sakakawea is not local, is not dependent just on North Dakota water, it's dependent on snowmelt water from the Rocky Mountains, and it's overflowing right now, right? But we know in times of drought then that if that water becomes restricted in here, Sakakawea can itself really go down in the amount of water that it could supply to any area. We haven't seen it dry up completely, but we've seen water levels go down pretty significantly, but not enough to not provide enough supply.